grabbing a link. Just grabbing a link. All right. So the plan for today was to go over the exam 2 short answers. We can do multiple choice. If you guys have individual questions, you can go ahead and ask me in Canvas, and I'll answer you in there. It's best if you send screenshots for that. If it's better, communicate, or just tell me which question number you want to talk about. It's fine. Just do it through Canvas messaging. Got my gold night shirt on today, so I gotta make the light golden, right? For the lamp here. There we go. We got the golden color today because the gold night shirt. So I figured it was appropriate. Honestly, I always use this color anyway because I think it looks like a softer light on the writing. But anyway. All right, grab some paper. Did anybody have any questions about anything before we start? I'm just pulling up the exam right now. If anybody's even watching this. All right, set up the view. There we go. And then this one, yeah. Trying to think how to set this up. I think I put myself on the bottom left. Come on. There we go. All right. So first question on the short answers here was to predict the product and draw the mechanism for both possible pathways. I was actually kind of nice on the grading on this one because I specified both possible pathways. So what I was specifically looking for here when I was writing it anyway, not necessarily when I was grading it. When I was writing this, I was hoping that you guys would recognize that I was looking for like an SN1, SN2, or E1, E2 type situation here. And this particular one is going to be the monomolecular route, and the reason why, trying to fix my camera here. Hang on. It's going to be the monomolecular route for the structure of the substrate here. It's the first giveaway. First off, it's tertiary, and then it's also benzylic. So you have both those factors favoring the formation of a carbocation. So you also could have shorthanded this a little bit. So the benzene ring is commonly shorthanded as pH. And for the sake of simplicity of the mechanism, stereochem of the starting compound doesn't really matter all that much. So you could have started it off flat. And let me just switch the view again. There we go. And we're reacting with Nash. All right, so first things first, you want to go ahead and show the leaving group leaving. Once again, this is monomolecular. Like that. So then you get the formation of the carbocation. And once again, I said when I first started this problem that this is benzylic. Rather than stabilized, it's also tertiary. So both these alone tell me that it is SN1, E1. All right. So now what you do is you could have shown resonance here. For the sake of time, I'm not going to show them here. I didn't. Only a handful of you guys did this part anyway, so I didn't mark off for it. But I did ask about draw resonance structures of the intermediate. This is what I was looking for when I was writing it, not necessarily when I was grading it. All right. So next thing we do here is we can show two different pathways. So I can go ahead and show the SN1 route first. This is the case where we can draw the lone pairs on the SH negative plus on sodium. And I use purple, so attack the carbocation like so. And then this is the chiral center. So stereochemistry. And don't forget that you get a racemic mixture, so you want to write plus enantiomer there, or plus En for short. All right, so there was the first one. Oh wait, so sorry, the next pathway that most people actually forgot to draw. I didn't mark off for it though. I felt like I was being nice this morning, grading your exams. But you could have shown the SH minus ion acting as a base instead. This would be a negative there. It's showing up very well. Negative. So just slide that up. So then you attack here. Boom. Double bond. And then this is your major product here. Like that. And then minor products would have been double bond here, minor, and then double bond where it's a cis alkene would have been another minor product possible too. So, all right. So there's that one. Next one here is asking you, it's number 2. So just pull it up on the screen real quick so for the sake of the video. All right, number 2 was draw the mechanism for the following dehydration. Assume the reaction is aqueous. All right, so here, what you could have shown here, because the reaction is aqueous, instead of using H2SO4 for your acid, I was fine if you just wrote H+, or if you wrote H3O+. I was even fine to put H2SO4. But honestly, if it's in water, it's going to be the water version, basically. So it's going to be hydronium. All right, so presenter camera. So I'm just going to go ahead and use it as H3O+, because I think that's the most right way to do this. So I believe the OH was here. So let me just double check. Yep. No rearrangements in this one. No rearrangements at all. So here, and then if the H2SO4 reacts with water, you'll generate hydronium. Like that. And then first step, protonation, makes it a better leaving group by doing that. OH2 plus. And then here, now you need to make the choice whether or not it's going to be like E1 or E2. Typically these are E1. We do have it. We will have a tertiary carbocation here. So yeah, definitely E1 route. So then the loss of water, dehydration. We lost water. Like that. And then you want to choose the H that'll give you the most substituted product here. And that's this one. And then for the base, I would use H2O. So I believe I actually marked off people for using the bisulfate ion as the base here. The reason why is just want to face the camera real quick. You guys should have learned in freshman chemistry that H2SO4 is a very strong acid. I also specifically mentioned that during with the acid-base section when doing the stuff also with elimination. The reason why you don't want to use the bisulfate ion is because, once again, it's the conjugate base of a very strong acid, which means its basic properties are very, very low. So the thing that's in solution that's definitely more basic is water. And you also regenerate the H3O plus catalyst at the end. Remember, regenerate the catalyst. The H2SO4 is effectively a catalyst here. All right, so with that in mind, I think it was like 1 or 2 points. I don't remember exactly offhand, but looks like I'm lagging. I was lagging just now. Sorry about that. Let's go back to this. So I'm going to add that little note here. Not HSO4 minus. That was the mistake, the bisulfate ion I was talking about. All right, so go ahead and show your last step at E1. Boom, boom, get the double bond. And then you're always going to get the Zastev product here, most substituted. You can only get the Hoffman product if you're doing E2 eliminations. All right, and that was number 2 on the short answers. All right, so moving along here, let's go ahead and pull the browser back up. And we just hide this. I think let's use the presenter camera and not try to get it all going out here at the same time. All right, so this was the formation of an alkyl halide. You are going to have basically an SN2 here. Yeah, I definitely had a lot of SN1, SN2 on this exam. So number 3. Let me double check my carbons. I think that's right. Yep. 1, 2, and then OH. Yeah, that's right. Okay. I think I'm missing a carbon, but no, that's right. Okay, so you are reacting with this with HBr. I think I showed you this in class, how we can basically trade out an OH for the Br. And the mechanism will be either SN1 or SN2, depending on the substitution on the substrate. This is a primary substrate, so SN2. But the first thing we have to do here is protonate, because OH is a poor leaving group. So that's what the H is going to do here. Acid-base reaction. So boom, boom, boom. H2O leaving group. And then you don't want to show it leaving on its own. And the reason why, once again, it's primary. You don't want to show primary carbocations in your mechanism unless they are resonance stabilized. That's the only time they're okay. So basically, they're benzylic or allylic. This one is neither of those, so it's not okay. It's incorrect. All right, so like that. Backside attack, your SN2. We don't need to worry about stereochemistry in this one because that is not a chiral center. So there we go, like that. The other version I showed for you guys was how we can convert ethers back into 2 alkyl halides. Same kind of chemistry was happening here. All right, number 4, there was no mechanism, but I wanted you to predict products here. This was the halohydrin reaction during the addition section. I think it's even like the same example too. Yeah, I'm pretty sure it's, I'm trying to remember if I used a cyclohexene or a pentene during, we went over that. All right, we did not do the mechanism for this one. For those of you guys going on into your standard organic chem course, this is one that's for sure covered. But we don't do that. I don't cover this 220 really. I just go over predict products. So in predicting the product here, this is going to be an anti-addition. You know, one up, one down. And you're going to get an OH and a Br in each carbon. You need to make sure the OH goes more substituted. So the tip I gave you guys in class was to go ahead and draw the groups you're adding first. So OH, so this is going to be this carbon here. You need to make sure they're anti to each other. And then you tack on what was already on there. The methyl was already on there. So that is the correct stereochemistry of that compound, properly showing a anti-addition. All right, and then you need the enantiomer. I was accepting just plus EN for this. But if you, just for the sake of completion, to make sure that you guys are, you know, some people wrote one enantiomer, some people wrote the other. So I want to make sure that both groups are seeing that they got the right answer. So here was the other variation of it. The key is making sure the OH and the Br are going opposite directions. Yep, so there's the enantiomer there. All right, so let's go ahead and take a look at the next question. Here's the resonance question, which I had a few questions about, like while while the exam was still live. I had 3 questions about this. So I was like, I'm not going to answer these questions until after it's due. Yeah, so yeah, a bunch of people were asking me to answer number 5, the resonance question, like a day before it was due. Not happening, guys. Just saying. All right, so this is the question here. The following, I tell you that it's aromatic. In the past, I used to ask students if this was aromatic or not, and most people got it incorrect, but I started this basically now. I tell you it's aromatic, tell me why. So I was specifically looking for, you can make a benzene-like resonance here. I was looking for that, or you can do it piecewise, which was much harder. And I think those that got it correct, most people that got it correct did it the hard way, I felt, to explain this. I did also mention there a brief verbal rationale. I was looking for the mention of Huckel's rules. So that was the planar, you know, the continuous pi cloud, that kind of stuff. 4 and plus 2, remember all those rules we went through? So let's go ahead and take a look now. I just want to go ahead and what I was thinking when I was writing it, what I was hoping you guys would come up with. So I'm going to copy the compound here. You're going to see that with the 2 arrow pushes with the resonance, it'll look sort of like benzene in the middle. Yeah, we got the ester group. So I always recommend that if you're doing resonance and you have a carbonyl-carbon, that's always your starting point. It's a very common starting point, and you can go to a lot of directions with many compounds for this. So that. And don't forget your non-zero formal charges. We now have a charge separation here. So 3 lone pairs and a negative, and then plus here. Oh, this is oxygen. And then I'm going to include these lone pairs here. Like that. All right, almost there. So we have the plus charge there, electron rich. This is going to naturally do this. Similar to how the carbonyl does that also. So it's very similar. This is pretty typical for resonance in esters. Double bond is now there, 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 and I'm going to include lone pairs there. All right, so we basically kind of sort of have a benzene in the middle, that ring now. We have that typical double, single, double around 6-membered ring, just like benzene. The key here in making sure you're following Huckel's rules is that you account for only what you're moving for the actual aromatic part. So yeah, we had to move these electrons around like this one first. But when I do the aromatic resonance, this lone pair from earlier is not going to be part of that resonance. Remember, you only include what is part of the resonance. And to show that, you basically want to show like your typical benzene where it all goes 3 at once. And then I mentioned earlier, a lot of you guys did like 1 arrow at a time. That is also correct, but it wasn't necessarily what I was looking for. This is an adequate explanation of the aromaticity. We got the full 360 going on here. And it also has 6 electrons, which satisfies the 4 and plus 2 criteria. Like that. So these two are what I was looking for, these 2 guys. Like that. All right, once again, this molecule is planar, satisfies Huckel's rule by having 6 pi electrons in continuous pi cloud. And that's it. All right, and that was number 5. All right, check something real quick. All right, check something real quick. All right, so take a look at the next one. Remember, guys, if you guys have any, I see there's a couple of you guys watching right now. If you have any questions, remember you are welcome to use the Discord. Number 6 was a Diels-Alder question. It was predict the product. So there was a particular aspect of this question I was not being particular about in the grading. I do specifically mention there that the second line there, provide the structure of the product, assume excess molar equivalent of the nucleophile. And so remember, we have a diene and a dienophile. Here and here, right? We have this electron withdrawing group, the carbonyl-carbon. Because of this oxygen here, I would argue that this side is more reactive. But I said excess, so I wanted you to see, basically put this piece on both sides. But let me show you the most common answer that I was accepting, that students did. And then I'll show you what I was actually thinking about when the question was written. So I had to realize that like what I'm going for and what you guys end up putting on the paper are not always the same, and I will make adjustments to the grading criteria. That's also part of the reason why I don't typically put a point breakdown on the tests themselves, is because I often will alter them if I do that. I used to do that in the past where I put the point values and I would end up altering them almost every time. So I got sick of having to explain that to students. So I was like, I figure out the grade points after I kind of shuffle through your exams a little bit and get an idea of how you guys did. All right, so I recommended in class to draw it kind of like Pac-Man style, kind of like munching towards the other compound. You kind of see where it's going to connect. They're going to connect here and here, like so. We're going to get a 6-membered ring. The new double bond is going to go here on that part of the ring. So let's go ahead and draw. So cyclohexene, boom, that's the new double bond. And then the rest of the molecule that was already there. Right, that was 1 molar equivalent. The second molar equivalent would add to this side. I feel that even though that's the donating group there, we have 2 withdrawing groups. I feel that this probably would still react if there was enough heat around. So let's go ahead and go with that. So other side, I think 1 person did this, remember right? So good job to that 1 person. There we go. That's supposed to be a CH3 there. It's not showing up very well. Yeah, that's CH3. All right, that was number 6. Let's take a look at number 7. All right, number 7, the last and the most entertaining one for you all, the synthesis question. Okay, so this is a 2-step synthesis, guys. We did one just like this in one of my lectures. That was the issue of whether the groups were adding syn or anti, whether the bond was trans or cis to start with. So looking at the orientation of these guys, notice how they're anti to each other. It works out when you're doing the halohydrin reaction. These are always going to be anti to each other. So in order for them to be anti in the Fischer conformation, which is what this side is showing. Oops, sorry, not showing it on the screen. There, sorry, this side right here is in the Fischer conformation. That means that it came from a cis alkene. So we had to turn this to a cis alkene first, and then do the halohydrin reaction. That's all there was to it, guys. Most people miss this question, or just left it blank, which made me sad when grading it. They didn't even try. The conditions to get to the cis double bond, this was H2 palladium with Lindlar's catalyst. Or H2 Lindlar's is fine. And let me just actually fill that in. A few of you guys did this here, but I just specifically mentioned what Lindlar's was. It's palladium with calcium carbonate. Remember, that makes it that it's a less strong catalyst, so you get less result. Less hydrogenation. All right, and then the next step here was just simply Br2 in water. You are going to get an anti-addition. But if you think about it, if you look at this one from the top perspective, this looks like OH is left, Br is right. Like that. And then you would also have the enantiomer. So plus En. But that one was the target, is that one. So it was just 2 steps. Most commonly, I saw students, what they were doing was they did this one here was the sodium and, sorry, the NaNH2 with sodium metal. That was the most common mistake. So, all right. So there's the exam. They are graded now. They were out of 60 points. I believe they're like, most were worth 9, some were worth 8, just basically to make the total 60. But every question was worth 9 or 8. And I did put in the comments, so if you actually go to the assignment itself, you want to see why I docked points. I actually wrote in the little rubric thing why you were docked points. So it's things like non-zero formal charge is missing, mechanism has a mistake in it, that kind of thing. It's all in the comments for your individual assignment. So, all right. So the next part I want to do for class here today is I kind of wanted to look at some of those aromatic reactions that we kind of didn't get a chance to go to last week. There was that worksheet that I wasn't collecting. that had the aromatic page on it that you guys were supposed to work on. And then there was the latter part which had all the aromatic reactions on it. Yeah, so it looks like it was worksheet 2.5, I believe. No problem. Yeah, so I wanted to work through these problems here. All right. You know what? Actually, let me go. I need to go grab my lab manual because, yeah, if you guys have not seen the handout yet for the nitration lab, that is literally my lecture notes compressed into the lab manual. So hang on 1 second. I need to go grab my lab manual. Where did I put it? Uh-oh. Uh-oh. I think it's my backpack. Maybe? Oh my goodness. Oh! There's my desk right in front of me. Oh my goodness. I forgot that I put it away in the desk. Alright, so lab manual. You guys may have purchased it. If not, it's all online. But alright, so that was experiment number, where is it? Nitration is 97. Alright, here we go. So switch over to this view. Alright, so here you guys actually have like almost like a textbook for this chapter. So this is literally my lecture notes condensed. So the thing about the aromatic reactions, hopefully you guys got a chance to watch the video. Which thinking back on that video, it's kind of funny because if you actually watch that video, it's during a snow day. So it was like 2 years ago we did a snow day because, yeah, it was literally snowing in Las Vegas. And traffic was crazy. And I was getting a lot of emails saying, please cancel class, teach us on YouTube. So that's what I did. I did the whole lecture on YouTube for that week, actually. But anyway, the basic idea on how these aromatic reactions work is there's two issues that happen here. We saw last section that aromatic rings are highly favored in nature. So they require a lot of prodding to get them to want to react because they don't want to react very much. So there's two main factors that can happen here. The first is that you have if you have an activated group on the benzene ring or a deactivating group, that can affect the reactivity. So in this mechanism we're seeing here, I'm looking like right here, we are seeing that benzene is acting as a nucleophile. So anything that donates electrons to this ring will make it a stronger nucleophile, therefore more reactive. Withdrawing groups do the opposite effect. So withdrawing groups like nitro groups, for example, the resonance on those will pull electrons out of the ring. So what's happening here is less reactive. After that, you do have the auranium ion, which does have resonance stability, allowing it to actually form due to the resonance here. It's still relatively high energy compared to the starting compound. So you still need either a strong electrophile or this is very strongly activated for it to work. Anyway, when you get to the last step of the resonance, that's literally an E1. So that's not a new reaction here, guys. That's literally an E1. So at this point, E1. The part leading. So I kind of think I kind of think of it as like a combination of the additions and eliminations together in terms of the concepts that you go over. So here we're seeing a pi bond of the nucleophile. We saw that during the addition chapter. And then this exact arrow push with E1, the end part of E1. All right, in this group, there are 5 reactions that I wanted you guys to go over. I do want to point out these are not all of them. These are just the classic ones that everybody teaches for the different reactions here. So you have sulfonation, bromination, nitration, alkylation, and acylation. These last two, the alkylation and acylation, add new carbon groups, and they are collectively referred to as the Friedel-Crafts. I do, however, give you the specific mechanism for the nitrate reaction. So here you have the formation of the nitronium ion. Hopefully you guys got a chance to watch the other video. It goes into a lot more detail. I'm not going into all the detail here. But we have the nitronium ion forming, and then it literally just follows this mechanism. Oops, my pencil. It follows that mechanism. So just put NO2 plus there, and that's pretty much it. That was number 3 on that worksheet, was asking for the nitration, I believe. Yep. So it's already in the it's in the handout. The next one here, though, I did want to quickly do. It says to provide the energy diagram for the EAS portion of number 3. Clearly label activation energies, intermediates, blah 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 blah. Okay. It's actually going to look similar to it's technically has 2-step mechanism, so it's going to look just like your E1 did, or SN1, the monomolecular one. You have the formation of the carbocation, which in this case is the arenium ion, and then you have it going down to the product here. I would specify. So remember these graphs, the way they worked was we had energy on the Y, and then we had reaction progress on the X, also referred to as reaction coordinate. There. Because you're basically breaking a benzene, sort of, you're basically making it not aromatic anymore. You do have a very high energy of activation for this reaction. That's why we typically use really strong electrophiles for catalysts here, like that iron compound, for example. That's where the arenium ion exists. The carbocation is there, and then down to products like that, just like the SN1 and the E1. All right. So number 5 is the challenging page. I think it's the one I wanted to do. Wait, yeah. Yeah, I wanted to go ahead and work through number 5, and then if you guys have any other questions about this particular section, you can go ahead and ask me. So let's take a look at number 5. All right, so do I have that list here? Hang on, let me double check my thing here. It's in the notes. So it's useful to have a list of what group is what, whether it's activating or deactivating, orthopara-director or meta-director for problems like this. So the short version of this, you should have watched the video already, the longer one. The short version is that if you're doing a reaction on a benzene compound that already has a group, the group already on there will affect where the next group goes. And the analogy I believe I used in the video was the order you add things in the kitchen when you cook does matter. And it turns out in chemistry it does matter too. So you are technically doing chemistry in the kitchen during then, right? So, all right, let me put my face back over here. All right, so let's go ahead and do a couple of these. So these are all starting from benzene. The target had a methyl and a chlorine para to each other, was the starting one. The thing here is that these are both orthopara-directors. Remember, halogens were the weirdo exception that they're. So let me just backpedal a little bit. So donating groups typically orthopara-direct, and then withdrawing groups typically meta-direct. The one oddball is halogens, because they kind of fall in the middle of the road, whether they're donating or withdrawing. They do technically fall on the withdrawing side, though, just slightly. And what ends up happening here is that they are withdrawing groups with the orthopara-direct. So you also have it. So technically, either order can go first. The better order, I would say, would be the chlorine first. And it needs a catalyst. You need iron 3 chloride for this. You want to match the halogens, otherwise you might get bromine. If you use FeBr3, for example, you're gonna get bromines on there instead, mixed in with your chlorines. The reason why I chose this group is because we put a chlorine on there, so we don't typically have to worry too much about multiple substitutions when you're putting a withdrawing group on there. If you put the methyl group on there first, the resulting product is more reactive. So alkylations tend to lead to multiple alkylations because the product you're making is more reactive than what you started with. All right. So here we have an alkyl halide. We need to make this thing to a carbocation. In order to make things that don't normally form carbocations, we kind of force them to make carbocations, is we react them with aluminum trichloride. So this compound, the purpose of it is to, if you look at the video, of course, it shows you that it allows compounds to make carbocations. If the compound can make a carbocation on its own naturally, like it's a tertiary halide, for example, or an allylic halide, sometimes you don't even need the aluminum. All you just need is throw it in water; it'll ionize. So that's not going to ionize because of the fact that it's a methyl. Methyl carbocations are not going to form naturally. We can force them to happen though with the aluminum compound, and that's the target. Like that for the first one. All right, the next one here. Oop, question. No. So once again, starting from benzene, I'm looking at the second target. Let me just pull the page up here. So this one, they are meta substituted here, so the order does matter. So this is a meta director. This is an orthopara director. You want to put the meta director on there first. So this group goes first, then this group. So the acyl group, acylation first, then the alkyl group, alkylation second. So let's go ahead and switch back over. So starting off, this is the corresponding halide that we need. And we'll get acetophenone from this, which is that one, acetophenone. But yeah, I was telling you before about how creative chemists are with naming. Acetyl, phenyl, acetophenone. Yep, very creative. Next step here is just that, and then we get that. Meta-methyl acetophenone. All right, the next one here is literally just reverse the order. So this next one here, in the actual lab, you would probably get multiple alkylations in the real world, but on paper, I'm typically fine. I would just specify 1 mole equivalent. This compound is to specify you only want 1 alkylation. And then this will orthopara direct this group. So flip the order. This one here requires the use of a redox reaction. So let me go ahead and show you this one. It's a little bit tricky. Hopefully you guys got a chance to see that reaction in the notes in the video. So we want a meta-substituted product here. The problem here is we have an NH2 on there. So the strategy I'm thinking here is we're going to put an NO2 on there first, and then we're going to basically put the methyl group on there next because nitro is a meta director. And it'll put it in the correct orientation, and then we can do a reduction on the nitro group. So here we get NO2. And then we will alkylate it. Same reaction as earlier. So that. And then the last, there's a couple different ways that this next reaction is shown. I think of them as being equivalent though. The way that we do it in lab at the college is we actually do this experiment. It is tin and HCl. Most textbooks show it as zinc and HCl. They both are fine here. I always show the tin one because that's the one we actually do that one in lab. And I know for a fact it works. It works every year. And you get NH2 like that. Like that. Next one requires the protecting group. Not too worried about using. Yeah, don't worry about the middle one on the bottom of the page there, guys, if you didn't figure it out. But you have to use the protecting group. And I feel that protecting groups are above the scope of this course. Next one here, you would just do a dibromination, so double brominate. It's an orthoparadirector director. And then this was not a typo. Notice here how it's missing the double bonds. To do that last step to get rid of the double bonds here, that would be high pressure and then just hydrogenation. So it's H2 palladium high pressure, H2 platinum high pressure, whatever. All right. So did you guys have any questions about anything? Look, the golden night is all sparkly in the light. I love this shirt. Target, in case anybody's wondering. This is where I got it, Target. You got to check and ask, second ask any question, otherwise I'm going to cut the stream here. Because I think we're at a good stopping point. Thank you. So next time, what I was planning on doing was we had to go over some carbonyl stuff. So we need to start this week's stuff. Get started early on this stuff, guys. This carbonyl chemistry gets crazy. So we are going to be doing additions to aldehydes and ketones. And then I plan on going over the entirety of the acyl substitution chapter. So normally, I told you before, I basically cherry pick certain things from Chem 241 and 242. I pulled the whole chapter of acyl substitution to drop into 220. So the entire chapter for acyl substitution is fair game for this course. For the aldehydes and ketones, just make sure we're clear here, I'll put it in the Discord chat too. It's going to be hydration, acetals and hemiacetals, and sulfur and nitrogen nucleophiles. You know what? Sorry, we're omitting the sulfur and nitrogen nucleophiles. So let me put it in the chat right now, so make sure I don't forget. For additions to aldehydes and ketones, only cover hydrates, acetals, and hemiacetals. There you go. So there's actually quite, if you're watching my videos, I typically go over those three first, and then I start doing the harder stuff. I'm not testing you guys on the harder stuff in that chapter. And then I also have videos up for the acyl substitution chapters. Remember, that whole chapter is fair game. So if you guys don't have any questions, I think we are at a really great stopping point, and I will do. I'm going to try to do most of the carbonyl chemistry next time. And then after that, we have to go over carbohydrates. I do a short version of carbohydrates with you guys. All right. Well, if there's no questions, then I'm going to go ahead and stop it here. And then once again, if you guys want to get in contact with me, remember we are talking through Canvas now. I'm only going to be using Discord, unfortunately, for I'm not going to say why, but I'm only going to be using Discord for talking during the stream. Other than that, talk to me through Canvas. All right, guys, have a good one. I will see you tomorrow. Stay safe, stay sane, stay cool.